Hi there. In this video, we are going to be talking about analyzing the motion of what's referred to typically as a full Atwood machine. An Atwood machine is two blocks. They're tied together by a rope, and that rope is strung over a pulley so that both blocks will move up and down and together. So as one goes up, the other goes down, and vice versa. So let's read the problem and get started. A 5.00 kilogram block and a 3.00 kilogram block are tied together by a rope, and the rope is draped over a pulley so that both blocks hang vertically. We will A, determine the system's acceleration. We will B, determine the magnitude of the tension in the rope. And we will C, determine how fast the 3.00 kilogram block is moving after it rises 1.25 meters, assuming that it starts from rest. Let's begin by determining the acceleration of the system. As with all good problem-solving things, we're going to start by drawing the situation, and here it is. We've got a pulley, we've got two blocks connected by rope draped over that pulley. I've made the 5 kilogram block look visually larger, called it M1, and the 3 kilogram block I called its mass M2. Next, I'm going to draw force diagrams for both blocks. Block 1's force diagram looks like this. There is a downward gravitational force pulling block 1 down. There is a string pulling back up on block 1, so there's an upward tension force on block 1 by the rope. Block 1 is both falling and getting faster as it falls, and so the net force needs to be in the downward direction, meaning that the downward gravitational force on block 1 by the earth is greater than the upward tension force on block 1 by the rope. And I've got my subscripts defined here. We are using the notation where 3 subscripts. The first subscript is the type of force, the second subscript is the feeler of the force, and the third subscript is the dealer of the force. So that's block 1. Let's go ahead and draw the force diagram for block 2. It looks something like this. We have an upward tension force pulling block 1 up, and the gravitational force on block 2 by the earth is pulling it down. And block 1 is both moving upward and getting faster in that direction, and so the acceleration net force for block 2 must be upward. And so there must be more net force upward than downward on block 2, meaning the tension force on block 2 is bigger than the downward gravitational force on block 2. We are assuming an idealized system where this pulley is massless and frictionless, and the rope itself has no mass. And for that reason, the tension will distribute itself evenly throughout the rope, meaning the tension on block 1 by the rope has the same magnitude, the same strength, as the tension on block 2 by the rope, as indicated by the double hash marks there. Next, we're going to choose our sign conventions. Remember that pulleys redirect force, redirect motion, and so we want to analyze this with sign conventions with a choice in coordinates that match what the pulley is doing. In other words, we're going to use a positive x-axis that curves around the pulley like this. That x-axis will start going up from block 2 because block 2 is moving in the upward direction. It has that acceleration in the upward direction as well. That pulley will then redirect our x-axis so that it's eventually pointing down by the time you get to block 1, and that's because block 1 has a downward acceleration. So that's going to be the helpful choice in sign conventions there. This pulley redirecting our x-axis means that for block 1, down is our positive x-axis, but for block 2, which is at the other end of the pulley, up is the positive x direction for block 2. Now, we need to choose a system if we're going to do an analysis. The system we are going to choose is the system that consists of both blocks and the rope that's connecting them. This is the choice to make. The key word here in the problem is that we're trying to find the acceleration of the system. So I'm going to choose the two object system and the rope connecting them. But even if I were just trying to find the acceleration of block 1 or the acceleration of block 2, I would still choose the two block system. And I would do that because this puts the rope internal to our system, and so we are able to find the acceleration without needing to worry about how much tension is in the string. And so even if I was just trying to find the acceleration of one of the blocks, I would still choose the two object system, knowing that the system acceleration is the same as the block 1 acceleration is the same as the block 2 acceleration. This is because they're tied to a rigid rope, which isn't stretching out or compressing, and so the motion of block 1 and motion of block 2 must match each other at all times. Now that I've got this set up, I'm going to make a list of my given information. For part A, that is the mass of block 1 is 5.00 kilograms, and the mass of block 2 is 3.00 kilograms. I could have also included that the Earth's gravitational field strength is 9.81 newtons per kilogram. And the thing I'm trying to find here in part A is the acceleration of the system, and that's going to be in our x direction as defined by that curve axis around the pulley. Since I know masses, I'll be able to do things with forces to find an acceleration. I'm probably going to set up a nice table here to help me analyze the forces on this system. I'll write net force equations based on the motion and based on the force diagram. I'll write vector and scalar equations. I'll simplify those down, and then I will combine them. Let's start by writing an equation based on the motion of this system. And this system is accelerating. And so when we find the net force, that must be equal to mass times acceleration. Of course, that's the net force in the x direction will equal mass times acceleration in the x direction. Now I'm going to look at my force diagram, or really force diagrams, plural, to add up all of the forces. I'm going to start by looking at the force diagram for block 1. And when I do that, I notice two forces in the x direction. I have the gravitational force on block 1 by the Earth, and I have the tension force on block 1 by the rope. Those are both in the vertical direction, which is our x-axis. So that's just one of the objects in the system. We can then go to the other object in the system, which is block 2, and look at the forces in the x direction for that. We have the tension force on block 2 by the rope, and we have the gravitational force on block 2 by the Earth. So these are all four forces exerted on our system in our x direction. Now, let's look at the tensions here. The tension on block 2 by the rope is up, which is the positive x direction for that block. And following things along, the tension on block 1 by the rope also up, but that's the negative direction for block 1. So we have a negative tension and a positive tension that have the same strength but point in opposite directions. And so when we add those two tensions together, they should add to 0, and in fact will add to 0. And so we don't need to worry about them. We can go ahead and add those to 0 right away, which is what I was trying to say earlier, which is by choosing to include the rope in our system, the tension is an internal force, and it's not going to affect the overall acceleration of the system. So this line, as written, you wouldn't necessarily need to write. You could just go ahead and assume that from the beginning. And what we'd be looking for really is that the net force in the x direction, this is what I'd be looking for when assessing your work. The external forces are the gravitational force on block 1 by the Earth and the gravitational force on block 2 by the Earth. Excuse me. Let's go ahead and write scalar equations. When I look at my net force scalar equations, I see one vector to worry about its direction based on the motion, and two vectors to worry about based on the force diagram. Looking at that, my acceleration will be in the positive direction because the object is getting faster the whole time, and so the acceleration is in the direction of motion, and I've chosen the x direction to be the direction of motion. And then the gravitational force on block 1 by the Earth is down, which is the positive x direction for block 1. The gravitational force on block 2 by the Earth is also down, but that's the negative direction for block 2. Another way to think about that is block 1, the heavier block's gravity, is helping things accelerate, and then block 2's gravity, the lighter block, is kind of working against the acceleration. Making this look a bit nicer, we can write this as net force equals mass times acceleration in the x direction, and we can write that just as gravity on block 1 minus gravity on block 2. And combining those, we see that the mass of our system times the acceleration in the x direction is equal to the gravitational force on block 1 by the Earth minus the gravitational force on block 2 by the Earth. Now we say, okay, what is it that I'm trying to solve for? Oh, it's the acceleration. Let's go ahead and look at this equation and isolate our unknown, which is a. I'll do that by dividing both sides by m, our system mass. And in so doing, we get an equation that looks like this. The gravitational force on 1 minus the gravitational force on 2, all divided by the mass. Now I'm pretty happy because my find is isolated. It's by itself on one side of the equal sign. And then I say to myself, okay, if everything on the other side of the equal sign is in my givens list, I'm ready to plug in numbers. Well, these variables aren't quite in my givens list yet, so I need to do a little bit more before I'm ready to plug in numbers. First thing I'm going to do is note that the gravitational force on block 1 by the Earth can be written as the mass of block 1 times the Earth's gravitational field strength, g. So we can make that substitution. Similarly, the gravitational force on block 2 by the Earth can be written as the mass of block 2 times the Earth's gravitational field strength, little g. And last but not least, this m, which m is it? Is it m1 or m2? No, it's neither of those. This came from net force is mass times acceleration. That m is always whatever your system's mass is. We chose the system that consisted of both blocks, so we should replace this m with the sum of both masses, m1 plus m2. And now I look at the equation I've written and I see, okay, everything is either an m1, an m2, or a little g. Those are all givens. My find is by itself. I am now ready to plug in numbers. So I'm going to go ahead and do that. I'm going to plug in the mass of block 1 is 5 kilograms to 3 significant figures. The mass of block 2 is 3 kilograms of 3 significant figures. The Earth's gravitational field strength, 9.81 newtons per kilogram. And then when I plug all of that into my calculator, I find that the magnitude of the acceleration in the x direction is 2.45 meters per second squared. Last step when I'm trying to solve for a vector is to, once I have the scalar magnitude, go ahead and put a vector arrow back above the symbol and indicate the direction information. So the acceleration in the x direction is 2.45 meters per second squared in our positive x direction, meaning down for block 1 and up for block 2. So that is how you find the acceleration. That's part A. Let's move on to part B. Determine the magnitude of the tension in the rope. Now, looking at the two-block system will no longer be helpful. If we want to know the tension, we need the tension to be an external force. I could choose block 1 or block 2, it doesn't matter. I'm going to go ahead and choose block 1 to be my system this time around. My given information is, again, the mass of each block, but also the find from a previous part of the problem becomes a given later in the problem. So I found the acceleration in part A as 2.45 meters per second squared, and now I can use that as a given in part B. And my goal is to find the tension in the string, or at least how strong the tension in the string is, which will be, I could write that as FT1R or FT2R because the tension is the same in both places. I'm looking for a force. I should probably go through a force problem solving method just like before. Based on the motion, the net force in the x direction is mass times acceleration. Here my system is just m1, so this m is now just m1 when I go to make substitutions later. Based on the force diagram for just block 1, in the x direction I have a gravitational force on block 1 by the Earth plus a tension force on block 1 by the rope. Scalar equation, I have 3 scalars to worry about, their direction. The acceleration vector is in the positive direction because we're speeding up in the direction of motion, and our positive x-axis is in the direction that things are moving. The gravitational force on block 1 by the Earth is down, and down is the positive x direction for block 1, and the tension force on block 1 by the rope is up, and up is our negative x direction for block 1. Simplifying this down looks like this, and then setting those two equal to each other, you see the mass times the acceleration is equal to the gravitational force on block 1 by the Earth minus the tension force on block 1 by the rope. What's the thing I'm looking for? The thing I'm looking for is tension. So let's go ahead and do a little bit of algebra to isolate the tension force. The first step will be to add the tension force over to the other side of the equal sign, leaving us with the tension force plus mass times acceleration is equal to the gravitational force. The tension force is not yet isolated. The last step will be to subtract mass times acceleration, this whole term, undo this addition, and subtract that over to the other side of the equal sign. And when we do that, we end up with the tension force is equal to the gravitational force minus mass times acceleration. My find is isolated. Am I ready to plug in numbers? Let's go look. No, not quite yet, because f sub g is not one of our things in our givens list, and m without a subscript also not in my givens list. So I'm not quite ready yet, but it's pretty easy to be ready. All I need to do is replace the gravitational force on block 1 with the mass of block 1 times the Earth's gravitational field strength. And I need to be more specific about my system mass now and put a subscript 1 on that mass because my system is just block 1. And now everything that is on the right side of the equal sign is in my givens list. Assuming I had written little g there, we can plug in some numbers. The mass of block 1 is 5 kilograms, the Earth's gravitational field strength 9.81 newtons per kilogram, and the acceleration 2.45 meters per second squared. And when we go ahead and plug in all of our values into a calculator, we find that the magnitude of the tension force is 36.8 newtons. Since I'm only looking for the magnitude or how strong the tension force is, I can go ahead and call it a day and box in my answer. I have completed part B. Let's go ahead now and look at part C of this problem. We are trying to determine how fast the 3 kilogram block is moving after it rises 1.25 meters, assuming that it starts from rest. Since we are analyzing the 3 kilogram block, that seems like the natural system to choose. Let's make a list of givens for part C. Here we have the same givens as part B plus a few new ones. We now know the tension force, so that find from part B becomes a given for part C. We can always choose our starting position to be 0 meters, which is the choice I'm going to make. And if we make that choice, the final position for our block will be 1.25 meters higher up. So the final position is 1.25 meters. We also know that the block starts from rest, so its initial velocity is 0 meters per second. So those are all the things in our givens. And what is our find? Our find is the final velocity, v. We don't know what that's going to be. And so the question is how fast. That's going to be a sort of motion thing. We're going to look at my motion equations from when we were studying motion earlier. Find one where v is the only thing we don't know and everything else is in our givens list. And if I go and do that, I might stumble across this equation, the time-independent equation, the one that tells us how fast we're going based on our displacement. And looking at this looks pretty good. That's my find. I do know the starting velocity. I do know the acceleration. And I didn't write it as displacement in my givens. I wrote it as final and initial position, but displacement is final minus initial. So if I just expand that displacement out as final velocity, or final position, pardon me, minus initial position, now all of my givens are on the right side of the equal sign. My find is on the left side of the equal sign. Now, you know the rule for my class at least, you're not allowed to plug in numbers until your find is isolated. There is one exception to that rule, and the exception is that you are allowed to plug in zeros early if it makes your life easier. So I'll go ahead and do that. I know the initial velocity is 0 meters per second, and I know the initial position is 0 meters. And so when I take 0 and square it, I'm left with 0, and this whole term goes away. And then when I take final position minus 0, this is going to be final position in the end. So this equation reduces down to v squared equals twice the acceleration times the final position. I can now go ahead and I'm almost there. I've got v squared by itself. If I want v by itself, I just got to take the square root. Excuse me again. And there we go. My final velocity is equal to the square root of 2 times the acceleration, which is in my givens, and position final, which is in my givens. And so I can go ahead and plug in those number values now. And when I do that, I find that the final velocity is 2.48 meters per second. And that'll be in our positive x direction because we chose the x direction to be the direction in which things are moving. So we've now reached the end of the problem. We found the acceleration of the system by analyzing the 2-block system. We found the tension in the rope by looking at just the system that consists of one of the blocks. We did block 1, but you could have done block 2. And finally, we used some motion equations to figure out how fast the block was going after it had risen a certain distance. Thank you for watching. I hope this was helpful. Thank you so much.